Let's take a look at the coastlines themselves. And there's many different ways that we can classify coastlines. What I like to do is a very simple classification. Is it an erosional coastline? Is it a depositional coastline? Erosional coastlines, like the picture of this rocky coastline on the top here, is a coast in which the dominant processes are those that remove coastal material, remove rock, remove sediment. In these cases, the amount of erosion is greater than the amount of deposition. So we still might be having sediment that's being deposited on that beach or on that coastline in the form of a beach, but we're removing more material from it than we're adding to it. We also have, on the opposite end of the spectrum, depositional coastlines. And here we see material that can be sediment or biologically derived material. Same thing for the erosional coastline. We can have biologically derived material as well. But here we see the accumulation of sediment. So in this case here, net overall erosion is less than net overall deposition. Once again, we might have some erosion occurring along this type of coastline, but depositional processes dominate. So you can see elements of both erosion and deposition on the beach, but it comes down to what is going in, how much is going in, and how much is being removed from within that particular coast. Erosional coasts, we see that there are many different processes, both land-based processes as well as marine processes, waves, currents, tides, that work together to create that erosional coastline. We'll take a look at a few of these processes and take a look after that at some of the features of an erosional coastline. What can cause erosion along a coastline? Well, there are a number of different things that can happen. We can have abrasion. So what happens is we have waves. Remember, waves can be sort of calm waves, storm waves, a lot of energy packed into them. They have the ability to pick up sediment that may be sitting along shore bar, sediment that's just sitting in slightly deeper water. They basically pick it up, and as the waves pound onto shore, in essence, it's throwing that rock, it's throwing that sediment up against the cliff. This is eventually going to wear down the cliff. So abrasion is one method by which we can have the breakdown of rocky cliffs. We're going to focus more on rocky cliffs here than anything else. We can also have attrition. And what happens is basically sediment keeps hitting each other and basically wears each other down, and becomes smaller and smoother. There are a few other things that can happen. We have something called corrosion. And corrosion, what happens is we have the breaking down of rock naturally by a chemical reaction. Some rocks, for example, rock limestone, made up of calcium carbonate, is very susceptible to slightly acidic solutions. So if we have a chemical reaction that makes that water slightly acidic, that's going to easily break down, easily erode away at that limestone cliff or that limestone rock that's comprising the shoreline. Just the simple action of waves hitting the shoreline, it doesn't have to have particles within it for abrasion to occur, but waves hitting coastline over and over again is eventually going to break apart the rock. One of the methods which it does this by is something that we call hydraulic pressure, which we'll take a look at in a couple of minutes. Okay, I lied. It hasn't been a couple of minutes, but let's take a look at hydraulic pressure. So rocks are not solid. We often think of rocks as solid, but if we take a closer look at a rock, we'll see there's usually lots of tiny little fractures within it, sometimes even larger fractures. Sometimes little holes, little pore spaces. Part of this is going to depend on what the rock type is. Some rocks are a little bit more together, have fewer fractures than other types, but there's always some sort of way for water to make its way generally into a rock, or most rocks. So what happens is if you have a wave, and you have the wave hitting a coastline here, or hitting the cliffs of a coastline, what you'll see is that within those cracks, the force of the wave hitting that coastline will basically push air into the cracks. What it does in essence is it compresses the water, it compresses air into the crack. So it's almost like using like a pressure washer, and you're shooting that water into the crack. This exerts a lot of pressure at the tip of the crack. As that wave falls back, as the water drains back out of these cracks, that air pressure is released, and that actually kind of sucks the rock out from the crack a little bit, enlarging the hole. So this hydraulic pressure works to enlarge these cracks, these pre-existing fractures in rock, making them bigger and bigger and bigger. Eventually gravity takes over, and any material, that rock, especially if it loses support from below, is going to fall back down into the water and possibly be carried away by waves, or picked up by waves and then pounded into that cliff again, further increasing the cycle of weathering and erosion. Here's a picture, rocks, a rocky cliff sort of in real life, and we'll see sometimes what type of rock it is matters. For example, we have a rock here on the bottom of sandstone and shale. Sandstone and shale, these are both sedimentary rocks. They're layered down, they're created in a series of layers of sediment laid down one on top of the other. What happens here is that because we have sort of all these beds, it's something called horizontal bedding. There's a lot of little horizontal fractures, horizontal planes in it, as well as vertical planes. Joint is just another word for fracture in geology. Water can make its way through these cracks and fractures. If we're in an area that's gets below freezing, that water can freeze, and basically as it freezes, we know that water expands by 9% when it freezes. It forces or cracks those rocks open. Even heating can sometimes cause differential expansion of minerals in the rock. So minerals will expand differently at different rates when they're heated up. This will cause further cracking of the rock, precipitation, rain, anything that actually can help that weathering and the erosion do the most work, especially at the weakest points in the rock, will make the rocks easier to break apart. Once you start to have a rock break apart, especially in a cliff setting, then gravity can pull that broken rock down. It's much easier for gravity to pull that broken rock down, and then it's transported away by wave activity, especially during storms if they're larger bits of rock. Here's a picture of a type of sedimentary rock along an erosional coastline. As you can see here, it's been undercut by wave activity, by possibly rocks being banged up against the cliffs or that bit of rock outcrop there during storm activity. You can see how many different ways there is for water to enter the rock. Both seawater as well as fresh water. There's a lot of pores, a lot of holes. So you can easily imagine that water entering it, if that water freezes, it's going to push that rock apart. The other thing we see here is the presence of grass on the surface. Remember, we said it was a combination of both marine processes and land or terrestrial-based processes that lead to erosional coastlines or aid in the formation of erosional coastlines. Well, in this case here, what the grass does, and if there's trees or bushes on the coastline, these have roots. And the roots, once again, act as a wedge. As that root grows down into the rock, especially if there's a little crack in the rock, it's essentially, as it grows, going to force that crack open, make it wider and wider and wider. Eventually the rock loses strength, it loses its sort of cohesiveness, and then it erodes, weathers and erodes. The vast majority of erosional coastlines tend to be rocky coastlines, and in fact, if you look at all the world's coastlines, would find somewhere up to about sometimes 80% of them will be rocky. Here in Nova Scotia, we get a really good evidence of this. We do have beaches along Nova Scotia, but most of our coastline is rocky. So beaches, very limited beach development. You do get them usually in the form of something called a pocket beach. We'll look at that in a second. Or is these really sort of thinner layers of sediment along the cliff base, which might extend further seaward as the tide goes out, especially here along the Bay of Fundy. Because it's an erosional coastline, what we see is that the rates of erosion far outweigh the rates of sedimentation or the rates of deposition. Finally, here in Canada, most of our coastline is rocky. This diagram nicely summarizes some of the more typical features of an erosional coastline. We see things such as exposed beach, also known as a pocket beach. We have sea arches, sea caves, sea stacks, headlands. So this is that part of the sort of the cliff that extends out into the water, and then obviously cliffs themselves. We'll take a look at some of these features and discuss how they form very briefly. The first feature of an erosional coastline that we'll look at is a wave-cut platform. And you might not always see a wave-cut platform. These will sometimes be underwater, especially during high tide. But here we see a really nice one exposed at low tide somewhere in southern Australia. So how do these platforms form? Well, what happens is originally a cliff would have been covering all of sort of this part of the platform that we see exposed here. So you can almost think of it as the basement of the cliff or the bottom part of the cliff. Over time, the cliff is eroded away. And when we see the cliff is eroded away, especially sort of at the very bottom, at the base of the cliff, this is where water is going to hit all the time, especially during high tide. Water is not going to hit up the upper parts of a cliff simply because the water level might not be that high. The water level won't be that high when we're at high tide mark. It might only get wet during extreme storm events. So most of the erosion of the cliff occurs at the bottom portion. And what happens is over time, through attrition, abrasion, hydraulic pressure, we create this notch at the base of the cliff. This notch is going to continue to grow and grow and grow. The sediment that's created as this notch is being created usually gets moved away by wave activity or by tidal activity, tidal currents as the tide goes out. But eventually what happens is support for the cliff is removed. So all that support that's holding the rest of the cliff up above top of it disappears. It's all being eroded and carried and transported away. And then gravity takes over again. Gravity is going to pull that rock down. It's going to cause a cliff collapse. That material is going to be hopefully moved away, and then we're left with a retreating cliff and this wave cut platform. So this wave cut platform represents the location where the cliffs actually used to be. You can look at it and find out where the wave cut platform actually starts or ends, depending on what way you're going. And this actually shows you where the wave cut or where the cliff extended at one point in the past history of that particular stretch of coastline. Erosional coastlines, rocky erosional coastlines tend to be very irregular in shape, given enough time, and here we're dealing with geological time, so we might have millions and millions of years. That shoreline might eventually be straightened by erosion. But what we see along these irregular shorelines is a series of headlands, so that's a bit of rock that's jutting out into the water, and then bays in between the headlands. And at sort of the end of the bay, the landward side of the bay, we might see this small pocket beach with sediment that's created by erosion along the cliffs that make up that particular coastline. If you want to look at this in more of a geological sense, usually we can see an irregular coastline of this type. It means that we're dealing with sort of strips or units, layers of rock of different rock types. Some rocks are more resistant to erosion, more resistant to being worn down than other rock types are. And it's responsible for sort of these irregularly shaped coastlines. So rocks of differing hardness and resistance. But this is a really typical view of a typical, a really classic view of a typical rocky erosional coastline. What will sometimes happen along the headlands, we see a lot of wave energy directed towards the headlands. It could also happen along some of the other cliffs as well, but more likely along the headlands, is we'll see the formation of sea caves. So there might be a little fracture, a little crack in the rock, lower down the cliff. Eventually through all these erosive processes that we're talking about, that whole fracture will be enlarged and form a sea cave. Sometimes if you take this to the extreme, and you may have a sea cave on either side of the headland, or you might just have that sea cave becoming larger and larger and larger, just one single sea cave. But eventually you might break on through to the other side. There's a really bad Doors reference. And you'll have the formation of a sea arch, like we see in these images from off the coast of Quebec here. So these sea arches, once again, this would have been a former headland. A lot of erosion, a lot of weathering is going along, especially along areas of weakness caused by fractures in the rock or by what we call bedding planes in the rock. Those are actually the sort of the lines you see in the rock that are either horizontal or dip slightly horizontal, or slightly dipping in the horizontal sense, and you get the creation of the sea arches. Eventually, if that material, so you see the sea arch right there, there's no support for the rock over top of it. Eventually, if that support removal of the support is great enough, the rock can collapse and we're left behind with something that we call a sea stack, sort of an isolated little mini island of rock very close or just offshore of the coastline or from the cliff. And here we have some pictures of different arches and sea stacks along sort of the eastern part of Canada, extending from Quebec and the Gulf of St. Lawrence all the way to New Brunswick as well as Nova Scotia. A series of sea stacks, a series of sea arches. Eventually these sea arches, especially from Perce Rock in Quebec, you can see a sea stack off to the right there. And eventually the section that just to the right of the sea arch that you see, eventually over time that will become a sea stack as well. And just some more views of some sea stacks, as well as the Hopewell Rocks, New Brunswick. More well known because this is a place where you can sort of walk on the sea floor as the tide goes out. But you can also hear not only sea stacks, but a wave cut platform that some of these sea stacks are sitting on top of. Now let's move on to depositional coasts. And one of the most dominant features of a depositional coast is a beach. Not only do we see beaches, but we also see features such as spits, tombolos, barrier islands, and deltas. And there's a few other features as well that we won't look at in this module. One of the things to keep in mind is a lot of these features are created, usually with the exception of a delta, are created by longshore drift, and that movement of sediment parallel to the coastline. So let's take a look at beaches. Beaches, as I said previously, a main feature of depositional coastlines. And we're talking about small little beaches, but we're talking about long, extensive beaches that go on for miles or kilometers, and kilometers. They're dominated for the most part by sediments. These can be finer, smaller grain sediments, or they can be large, coarser grain sediments, but it's not solid rock. It's not a rocky cliff that we saw with our rocky coastlines, our rocky erosional coastlines. What is a beach? Well, a beach is an accumulation of unconsolidated sand or gravel. So once again, this is just loose material that extends from the average low tide mark. So, where does the tide go out to on average? To the uppermost extent of wave impact. So here we're looking at a beach off the western coast of Australia, Cottesloe Beach in Perth. And basically we're looking at the beach, we're looking at low tide here. The uppermost part of the beach would be just slightly off the picture there, just a little bit above the blue tent that you see on the left-hand edge. The composition of beaches is variable. We've talked a little bit about sediment composition in a much earlier module. Here we see some examples here. Different types of beach sediment represents different types of sources that are feeding that beach. Here in figure A, we have this sort of black basaltic sand. This is from a volcanic source on the island of Maui. B, here we see these little green things and the brown things are rounded glass fragments. This is in North Carolina near Fort Bragg. And what's happened there is an old garbage dump is being actively eroded away. And as it does, it creates these rounded sort of beads of glass that then get deposited in a beach further along the coastline. And then finally, we see beaches that, basically a mix of both terrestrial and biological particles. Here, the red arrows show where the shell fragments are. So beaches, the important thing to remember here, comes in a wide shape of different compositions. Not all beaches, or not every beach on the planet is made up of exactly the same type of sand or material. We've already talked a little bit about this when we talked about sediment transport along coastlines, and this is how sediment moves on the beach. It moves sort of as swash, that's water moving up onto the beach. That swash will pick up particles, it will carry sand particles onto the shore. It will either deposit them there or it will transport them back down the shore in the form of backwash. Backwash is the water returning to the beach. The purpose of the swash, if it keeps bringing particles on shore, the backwash doesn't remove those particles, is the beach over time will progressively get steeper and steeper and steeper. So we need a really good balancing act between the swash and the backwash to sort of maintain the typical sort of average slope of a beach. If we bring too much material out with backwash, not enough in with the swash, then we start to lose sediment and the beach starts to grow smaller and smaller and smaller. The size of the grains that comprise the sediment will also play a role in the movement of sediment within the beach. So if we're looking at finer grain sediment, so small little sand grains, what happens is water tends to easily move up and move back down the beach slope, with more sediment being carried away by the backwash. And why is this? Well, it's because with finer grain sediment, as that water moves up in the beach as swash, that water not only will move up the beach as swash and move back down as backwash, but that water will also move vertically and sink down into the beach, percolate down into the beach. So if you have a finer grain beach, it's much harder. There's less space for that water to sort of travel downwards in. So we have water both returning to the ocean as backwash, but we can also have water being pulled down by gravity down into sort of the subsurface of the beach face as well. If we have larger size sediments on the beach, then some of that water now is going to actually make it much easier down into the rock or the sediment that makes up the beach. If we have a lot of water returning into the ocean as a result of backwash, the potential for it to bring sediment back, to transport sediment off the beach is much greater. If we have water that washes up as swash, but then it percolates down to the subsurface of the beach into these coarser grained sediments, then we have less water returning as backwash, and the ability to transport and move sediment back down is decreased. So water moves easily through coarser grain sediments, backwash carries less sediment back into the beach, and what happens then is the beach becomes even steeper. So beaches made of coarser grain material usually are steeper than beaches made up of finer grain material. We can also see a difference in beaches between summer months and winter months. And that's because in winter months, we tend to have a lot more storm activity. This results in even larger storms. We have an increase in wave energy. So there's a lot more energy within the water to move material onshore and carry material offshore. More energy means that water is able to transport larger sized grains of rock. So in the wintertime, those larger sized grains of rock are brought up into the shoreline. Once again, because they're larger, there's a lot more pore space. Water is going to percolate down through it, and we're going to have less movement of that material, less backwash returning back to the water. So we're left with this accumulation of coarser grained rocks on the beach during the winter. During the summer, things tend to be a lot more calmer. We still get the occasional storm, but nothing like we'll experience in the winter. And what happens is we see sand, and this sand is usually stored just offshore during the winter time. But now the sand starts to be brought back up into the shoreline or back up into the beach. Because you're dealing with lower energy waves, it's much more difficult for the sand in this case to be dragged offshore, transported offshore, and our beach becomes covered with sand and starts to have a much shallower angle as well. So winter beaches tend to be steeper sloped, summer beaches tend to be shallower sloped. Here's a side view of what will happen on a beach. So once again, during the winter, lots of stormy weather. We get a much steeper beach face. The sand is stored offshore. In the summertime, calmer weather, we see that sand that's typically stored offshore during the winter. We're just dealing with coarser grained material up on the beach. That sand then gets moved back onto the beach, and we have a much shallower, sloping, and much sandier looking beach, typically in the summertime. We can still sometimes have a rocky beach,